At one of the previous videos we have learned how to use a transistor as an electric switch. At this video we will see how a transistor can be used to switch another one. In the most simple case, the base of the second transistor is connected to the collector of the first one via a series resistor. The base of the first transistor is connected to a pull-up resistor, hence it is turned on, meaning the resistance of the emitter-collector line is minimal. The voltage drop at the collector of the right and so the base of the left transistor is nearly zero, hence the second transistor is turned off. The LED above the transistor is lighted up if the device is turned on. By a push button, the emitter baseline of the right transistor can be bypassed. Thereby the right transistor gets turned off and so the voltage drop at the collector is increasing to almost the supply voltage. Via the coupling resistor the base voltage of the left transistor is increasing too, hence those device is turned on. If the push button is released, the circuit falls back to the initial state, because now the right transistor is turned on again via the pull-up resistor. If the button is pushed for a very short time, the left LED is flashing shortly, while the turn-off time of the right LED is hard to recognize. Let's alter the circuit slightly. Now not only the base of the second transistor is connected to the collector of the first one, but the base of the first transistor is also connected to the collector of the second one via another series resistor. Two push buttons can be used to bypass the emitter-collector lines of both transistors. Two LEDs connected to series resistors visualize the switching state of the transistors. The accordant LED is lighted up if the resistance of the transistor next to it is at its maximum, thus the device is turned off. At the initial state, the right transistor is turned off and almost the supply voltage can be detected at the accordant output clamp, by what the right LED is illuminated. The base of the left transistor is connected to the collector of the right one via the series resistor R1, so we can detect a voltage drop of approximately 0.6V. The left transistor is turned on, the voltage drop at the emitter-collector line is almost zero, hence the left LED is not illuminated. The potential at the base of the right transistor is pulled to nearly ground by the series resistor R2, hence this device is turned off by the left transistor. The situation is stable, while the left transistor is turned on, the right one gets turned off, providing a feedback voltage which sustains the switching state of the left transistor. What happens if the left button is pushed? Well, those switch provides a conductive connection between the base of the left transistor and the negative terminal of the voltage source, by what the base voltage is decreasing to 0V, while it was 0.6V beforehand. Thereby the left transistor is turned off and the collector voltage is increasing to nearly the supply voltage of the circuit. The potential at the base of the right transistor is increasing to 0.6V because of the loopback provided by the series resistor R2. Now the right transistor is turned on by the left one, which in turn pulls the base voltage of the left device to nearly ground. Even when releasing the push button, the state of the circuit is kept. The left transistor is still turned off by the right device, which is now turned on. When actuating the left push button once again, the state of the circuit doesn't alter, because the base voltage of the left transistor is already pulled to ground by the emitter-collector line of the right transistor. By pushing the right button, the emitter baseline of the right transistor is pulled to ground, hence those device is turned off. Via R1, the left transistor is now turned on, which in turn passes a loopback voltage of nearly 0V to the base of the right transistor via R2, turning those device off. The state of the circuit is also kept after releasing the push button. Pushing the right button again doesn't alter the state of the circuit. By pushing the left button, the left LED is turned on, while the right one is turned off. Those button is marked by an S, it is called the Z button. By pushing the right button, the left LED is turned off and the right one is turned on. Those button is marked by an R and it is called the reset button. By pushing the set button, the output Q is set to the supply voltage, while it is reset to 0V by pushing the reset button. Q' is called the inverting output of the circuit. While Q is set, meaning the output voltage matches the supply voltage, Q' is reset, meaning the output voltage is 0 and vice versa. Those circuit is called flip-flop, latch or bistable multivibrator. By using a flip-flop, even short pulses can be detected reliably. Pushing both buttons simultaneously results in a forbidden state. Now, the base voltage of both transistors is pulled to ground, by what both devices are turned off, hence both LEDs are lighted up. The feedback voltage via the coupling resistors is pulled to ground by the two switches. When releasing the buttons, the output Q locks at either on or off, depending on which button was released first. Again, the circuit is altered slightly. It is called monostable multivibrator. The coupling resistor at the base of the right transistor has been replaced by a capacitor, while another resistor is connected between the positive terminal of the supply voltage and the base pin. Just one switch is required to set the output Q. It is reset after a fixed time span. At the initial state, the right transistor is turned on, by what the base voltage of the left transistor is pulled to ground via the coupling resistor R3, hence this device is turned off. The base current of the right transistor is running from the positive terminal via R2, by what those state of the circuit is kept. What about the voltage across the capacitor at this stable state of the circuit? The left pin of the capacitor is connected to the collector of transistor 1, which is turned off, hence the potential at those pin equals nearly the supply voltage, 10.1V can be detected. The right side of the capacitor is connected to the base pin of transistor 2, which is turned on, hence a potential of approximately 0.6V is applied to those pin, like explained at the video about the properties of bipolar junction transistors. The resulting voltage drop is 9.5V, with the positive pole at the left side of the capacitor. By pushing the button S, the emitter baseline of transistor 2 gets shortened, and transistor 2 is turned off. Via the coupling resistor R3, the left transistor is turned on. The potential at both plates of the capacitor is altered by the fast switching operations. Let's remove the capacitor from the circuit and detect the altering voltage at both clamps of the device while the button is pushed. Prior to this, the detected voltage drop is 9.5V, while it is decreasing clearly when pushing the button. The left side is pulled to nearly ground via transistor 1, which is conductive. A voltage of just 0.1V can be detected. The right side of the capacitor is pulled to ground by the switch, which is conductive too. The detected voltage is 0V. The resulting voltage drop between the clamps of the capacitor is just 0.1V. The voltage across the capacitor is still 9.5V, by what there is a disequilibrium between charge and potential at the clamps of the device as soon as it is reinserted. Caused by those disequilibrium, electrons are entering the capacitor at the left plate while they are leaving the device at the right plate. Both plates of the capacitor are connected to the negative terminal of the voltage source via low resistance devices. Hence a discharging current is running for a short span of time as soon as the capacitor is reinserted, until the voltage across the device is decreasing from 9.5V to 0.1V. As you can see, the left LED is flashing while the discharging current is running. Of course, those process occurs also if the capacitor is not removed from the circuit before pushing the button. A discharging current is running through the capacitor until the voltage drops down to the measured value of 0.1V. For a short span of time you can see both LEDs lighted up. If the button is released, once more a disequilibrium in potential originates from the charge accumulated inside of the capacitor. The left plate of the capacitor is still pulled to nearly ground by transistor 1, while the right plate is now connected to the positive terminal of the supply voltage via the resistor R2. An equivalent circuit looks more simple. Note that the negative pole of the capacitor is connected to the base pin of transistor 2. The charging procedure starts with a potential of -0.1V at the base of those transistors. Now electrons are running through a low resistance to the left at the equivalent circuit to the lower plate of the capacitor. The right, respectively upper plate, is connected to R2, hence electrons are running through a high resistance to the positive terminal of the supply voltage. The polarity of the charge current is different from the initial state of the capacitor. During the charging operation, the voltage across the capacitor and so the base voltage of the right transistor is increasing, starting with -0.1V, now in relation from the left to the right plate. If the voltage across the capacitor from the left to the right plate exceeds a potential of +0.6V, the resistance of the emitter-collector line of transistor 2 is decreasing clearly. The transistor is turned on again. Via the coupling resistor R3, the left transistor is turned off, whereby the potential at the clamps of the capacitor caused by the supply voltage is altered again. The potential at the left plate of the capacitor is increasing from nearly 0V to nearly the value of the supply voltage, while those at the right plate is still around 0.6V. The resulting voltage drop at the capacitor caused by the supply voltage is +9.5V, while those across the device is still around -0.5V. Remember that the switching operation is very fast. Note that the polarity at the clamps of the capacitor altered again. Now the positive pole is at the left side of the device, like at the beginning of the procedure, while inside of the capacitor there is still a surplus of electrons at the left plate. The disequilibrium is balanced at the left plate by a current running through R1 and at the right plate by a current running through the base of the right transistor. There is a positive feedback loop. With increasing base current, the resistance of transistor 2 is decreasing, causing an increasing resistance of transistor 1 via the coupling resistor R3, which in turn lifts the left plate of the capacitor to a higher potential and so provides a higher base current through transistor 2, driven by the disequilibrium of charge cumulated inside of the capacitor. Now the capacitor gets charged with the initial polarity via R1, respectively the base of the right transistor. The polarity inside of the capacitor alters during the procedure and finally the initial state is reached. Without the capacitor connected to the circuit, where at a voltage of -0.1V can be detected, the processes are running with nearly no lag of time. The charging procedure, limited by the current running through R2, affects the turn-on time of the left transistor. When reinserting the capacitor after the button was released, we can see the left LED going out for a short span of time. Let's have a closer look at the processes at the capacitor while actuating the push button. Like explained, there is a discharging current running for a short span of time. What is happening if the button is released before the capacitor is discharged completely? Well, the voltage drop across the capacitor from the right to the left plate is higher than 0.1V, depending on the time span the switch was closed. The charging procedure starts with a voltage of -4.5V at the base pin of the right transistor. Now, the time span required to reach a voltage drop of +0.6V at the base of transistor 2 increases clearly. The circuit can be altered with another capacitor, respectively resistor, to get just a small pulse while actuating the push button. By pushing the button, capacitor 2 is switched in parallel to the base of transistor 2, hence the voltage drops to 0 because the capacitor was discharged beforehand. As long as the button is pushed, capacitor 2 gets charged via R2 and capacitor 1. The lower the capacitance of capacitor 2, it must be clearly lower than those of capacitor 1, the faster the charging procedure, and so the higher the voltage across the device after a very short span of time, resulting in a short turn-off time of transistor 2. When the button is released, capacitor 2 gets discharged via R6, whose resistance should be clearly higher than those of R2. So the initial state of capacitor 2 is reached. Now the turn-on time of the output clamp Q is independent from the time span the push button was activated. When replacing the coupling resistor R3 of the monostable multivibrator by a second capacitor resistor network, the resulting circuit is an R-stable multivibrator. In contrast to the monostable multivibrator, the potential of two capacitors is altered by the contrarious switching operation of the transistors, and there is no stable state. The voltage curve at both capacitors is symmetric, so let's discover the progression at capacitor 2 while the left transistor is turned on and the right one is turned off. The voltage at the base of transistor 2 is lower than 0.6V, which is why the base current is very low, hence the resistance of the emitter collector line is very high. The left plate of capacitor number 2 is connected to the base pin of transistor 1, which is turned on, hence the potential is approximately plus 0.6V. The right plate of the capacitor is connected to the collector of transistor 2, which is turned off, hence the potential is around the supply voltage. The total voltage across capacitor 2 from the left to the right plate is plus 7.0V. The potential at the right plate of capacitor 1 and so the base current of transistor 2 is increasing, because those side is connected to the positive supply voltage via R2. The situation inside of the circuit tilts around a potential of plus 0.6V. Now the right transistor is turned on, while the left one is turned off. The potential at the clamps of both transistors alters abruptly. Those at the right side of capacitor 2 is decreasing from nearly the supply voltage to just 0.4V, while the voltage across the capacitor is still around 7.0V. Those plate of the device is connected to the negative terminal of the supply voltage via the low resistance of the emitter collector line of transistor 2. The resulting potential at the left side of the capacitor and so the base of the left transistor is minus 6.6V. Analogous to the process at the monostable multivibrator, capacitor number 2 gets charged with altered polarity via R3. If the base voltage of transistor 1 increases to approximately 0.6V, the circuit tilts again. Now transistor number 1 is turned on while number 2 is turned off, consequently the potential at the clamps of the capacitor alters abruptly. The left plate is connected to the negative terminal of the supply voltage via the emitter baseline of transistor 1, which has a relative low resistance, while the right plate is connected to the positive terminal via R4. The resistance of the emitter collector line of transistor 2 is at its maximum, which is why the capacitor gets charged with the initial polarity via R4. The charging procedure starts with a potential of approximately minus 0.2V related from the left to the right plate. The voltage across the capacitor and so those at the collector of transistor 2 is increasing to nearly the supply voltage. Thereby the initial state of the circuit is reached and the procedure starts again. At the falling edge of the signal, the correspondent transistor is turned on, hence its resistance is minimal. Consequently, there's just a slight distortion of the signal at the lower end of the falling edge caused by the disequilibrium of charges inside of the capacitor. The slew rate at the rising edge is lower the higher the capacitance and the resistance of R1 respectively R4. The correspondent transistor is turned off, hence the resistance of the emitter collector line is at its maximum. Consequently, the charge equalization is done via R1 respectively R4, so the voltage is increasing slower the higher the resistance of those devices. There are several ways to build multivibrators. Here you can see an astable multivibrator using a single operational amplifier. The functionality is easy to understand while considering the functional principle of a Schmitt trigger treated at one of the previous videos. The input of the Schmitt trigger, which is identical to the inverting input of the operational amplifier, is connected to the output of the circuit via a resistor-capacitor network. While the potential at the capacitor, and so the input of the Schmitt trigger, is lower than the lower threshold, the output voltage equals the positive supply voltage of the circuit. Now, the capacitor gets charged via the resistor R3 until the upper threshold of the Schmitt trigger is reached. As a result, the output voltage of the operational amplifier tilts to the negative supply voltage. Now the capacitor gets charged with reverse polarity via R3 until the voltage across those devices reaches the lower threshold of the Schmitt trigger. The output voltage of the operational amplifier tilts to the positive supply voltage and the whole process starts again. Besides the lower number of required elements, an advantage of this multivibrator is the better quality of the output signal. Even at very low switching frequencies, the slew rate of the output signal is very high and there are almost no distortions. The whole stuff is written down at the project page. There you can find more wiring schemes of multivibrators and some mathematics enabling you to calculate your own circuits. Thanks for watching and I'll be back.